Hello everyone. As a new lecture series on chemical equilibrium, a thermodynamic approach was started. So in its second lecture, the subtopic is relation of Kp with Kc and Kx. Let's start with the ideal gas equation Pv equals to nRT, and then rearrange this equation in such a way that V is taken to the right hand side and put below N. So it can be written as P equals to N by V RT. Now N is the number of moles and V is the volume. Then this expression is actually number of moles per unit volume. That means it's the concentration. So this can also be replaced by C. C is concentration. So P is equals to CRT. So for any component, for example, say component A, we can write PA equals to CART, where PA is the partial pressure of component A and CA is the concentration of A. Then the expression can be written as PA equals to CART. If we take into consideration the mole fraction relationship, then it is the partial pressure over total pressure. As for example, take component A, then the mole fraction of A, XA, should be partial pressure of A by total pressure. So it is written as XA. Okay. Then if you rearrange this equation, then you can write small pa equals to XA into capital P. That means mole fraction of A into total pressure. So these two equations we shall utilize here in order to find out the relationship of Kp with Kc and Kp with Kx. First, we take Kp and Kc. So in order to do that, let's rewrite this equation Pa equals to CRT. Similarly, for other components also, we can apply this relationship in expressions of Kp as, this is the expression of Kp, partial pressure of P to the power number of moles of P, partial pressure of Q to the power number of moles of Q, partial pressure of R to the power number of R, and so on. That means all the products. And in the denominator, partial pressure of A to the power the mole fraction to the power the number of moles of A, partial pressure of B to the power number of moles of B, partial pressure of C to the power number of moles of C, into so on. Okay, now we have the expression of partial pressures in terms of concentration. So if it is P, partial pressure of P, then you can write it as concentration of C, concentration of P into RT, and then in its power the small letter p would go. Similarly, for Q also we can write CQRT whole to the power Q, and in the same way for the reactants also you can apply this equation, such as instead of Pa you have written CART, and this to this power the small letter a, that means the number of moles of A. This is CBRT, number of moles of B, and CCRT, number of moles of C. Here three types of C. All these C's are different. This C indicates concentration, this C indicates the name of the component, and this C indicates the number of moles of C. Okay, so these three C's are all different, such as here 3P. Okay, this P is partial pressure, this P is the name of the component, and this P is the number of moles of P. So you have to keep in mind all these things. We are writing the same letters, but they have different physical significances. Okay, that's a different thing. Okay, now move on to the main topic. Now let's separate the concentration terms and RT terms, and you would find that the concentration terms would have their respective number of moles into their powers, and along with RT you will have the stoichiometric difference. That means P plus Q plus R plus dot 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 minus A plus B plus C plus dot dot dot. Okay, so delta nu, it is nu, it is not V. Okay, it looks like V, but this is cursived V and this is Greek letter N. Okay, if you type Greek letter N, then it would appear like this. It is actually called nu. When you write it on your copy with the help of your pen, then move the look the movement of the cursor, this and this. Okay, like once again this and this is nu, such as H nu. Okay, so that nu. So here nu is delta nu is the number of difference of the number of moles of the products and the number of moles of the reactants. That means P plus Q plus R, small letter, minus within bracket A plus B plus C. Okay, dot dot dot. So we have the expression here in terms of concentration, and this is nothing but the expression of Kc. So Kp equals to Kc into RT whole to the power delta nu. So this is the relationship between Kp and Kc. And if you reverse this order, then you can also write Kc equals to Kp into RT whole to the power minus delta nu. Okay, so this is one relationship. Now let's borrow the relationship between partial pressure and mole fraction, this in the previous slide, this relationship, and let us apply to the expression of Kp. Okay, now instead of Pp we can write Xp into capital P. Okay, and as usual to its power the number of moles of P would go. So this expression is obtained. Now separate the mole fraction terms and separate the total pressure term, and its power, to its power you will get delta nu. So this is the actually expression of Kx. So instead of that you can write Kx, and so you will get the relationship Kp equals to Kx into P to the power delta nu. This is the relationship. Or in the reverse order you can write Kx equal to Kp into P to the power minus delta nu, where P is the total pressure of the system. Okay, so that's all for this lecture. Thank you. Have a nice day.